Hello, everybody. I'm happy to be here. And then, actually, I don't know very much about the glass things, but I learned a lot by joining this conference. Thanks for the discussion. I really enjoyed listening to your talks. And then today, my talk is again about this 5G issue, which is the future cellular mobile phone, which is coming already actually this year. And it's going to be much more relevant in the next years. And then industry is very keen on deploying this 5G. But there's the one big bottleneck when we are serving this 5G to the indoor users, which is this very high attenuation of the facade to provide the coverage for the users. So that's the motivation for us. And our work is the joint work between us, who is doing the 5G issues, radio issues, and then the Marko Makkonen from Lam-Iklat, who is expert on the glass side. So this is a fruitful collaboration, and then I'm happy to show this result with you. 5G, nowadays it's very required. It's almost everybody is right to get wide band connection, very high-speed connection everywhere. So we expect that it's usable in the train, in the building, during we are taking high-speed train, wherever. What is then the unique solution to realize this higher data rate? We use the higher radio frequencies to have wider bandwidth. And then we use like smaller coverage areas so that the users can enjoy a better data rate per area. So in practice, what it means, there are many radio frequency slots that the future wireless is going to use. Gigahertz, gigahertz, gigahertz. Presently, we are using up to 2 gigahertz. And then, as you have mentioned in the previous presentation, 5G first uses 3.5 gigs. In the future, we are going to use even 28 gigahertz, 10 times higher frequencies, because that allows us to have higher bandwidth. The higher bandwidth, wider bandwidth means that we can transfer more data. So this band just list of the bands just tells us that there are many bands that we need to support for indoor users. But then when we are thinking about the cellular systems that we enjoy now using this mobile phone, usually the data comes from outdoor. Not many people can enjoy the cellular connection from indoor because the operators do not want to install the base stations indoor, which is costly and then requires some negotiations with the building owners and so forth. Then we need to expect some penetration of the radio signals from outdoor to indoor. Then what happens? So this is the example of the attenuation due to 0.1 meter slab of concrete and then plasterboard. And then in the conventional cellular systems, the attenuation is like 1 dB, which is like 1 over 1.3 times in power, which is almost nothing. But if we are going to the higher frequency range where the 5G may be deployed, then the attenuation becomes much quickly increasing up to here 0.5 dBs maybe. Sorry, this is 5 dBs, this is 3 dBs and so forth. So we suffer from much more hue or much more attenuation when radio signals are penetrating indoors. And then if we are going to go further, like 100 gigahertz, which may be the case for 6G, 7G in the future wireless, then attenuation can be even higher, 1 over 10,000. So this is a very problematic thing for the operators, because even though we install the base stations outdoor, indoor users cannot enjoy the connectivity very much. Evidence coming from scientific papers. This shows that, This shows how much attenuation we measured for different frequencies, like 10 gigahertz, which is higher frequency than what we use now, around 10 dBs, 100 gigs, it can be even 40 dBs, which almost kills the indoor connectivity. And then depending on older building or or new building, then we have a different amount of the losses. So higher building, we kill more radio signals because we put the metallic film. And then Yuha's idea was to make slots on this metallic film so that radio signals coming in. Then our idea actually is not to use the metallic film, but then without being able to use the metallic film, can we really realize the same U value as we are realizing with the metallic film? So in order to analyze that one, we have some very complex mathematical formula. In, for example, the plane wave, the radio wave is incident from outdoor. It is penetrating through the glass, and then we have the transmitted field. And we want to get this transmitted field as big as possible. Then we can analyze how much is transmitted compared to the incident by a very simple formula that is available in this ITUR, this ITR recommendation. And then how much we can transmit is dependent on the incident angle of this wave, what is the field polarization of the wave, and then the material parameters of this glass. The glasses which we considered consist of those like 4 types. Clear floating glass, soft-coated, hard-coated, and then laminated glasses. And they are combined so that it represents some realistic windows which we are in use in practice. And then up to 4 glasses without coating. And then the glazing structure that we analyze is like described like this. For K, this means hard-coated glass with 4 millimeter thick, plus standard air gap 150 millimeters, plus 4 millimeters of the floating glass, 16 millimeters insulating gap filled with argon, and finally the soft-coated glass 4 millimeter thick. So this is our representation of the window or the glazing that we have to analyze the attenuation of the radio signals through it. And then actually the attenuation depends on incident angle. Attenuation depends on polarization of the field. So we just take the mean of different polarizations so that we define some representative value of the attenuation loss. And then we also optimized the electrical parameters of the glasses, soft coating, hard coating, and laminate so that we can get the right estimation of the attenuation of the radio signals. First, we try to simulate. We established a simulation tool for that purpose. And then first, we try to verify whether this tool provides us with the realistic estimate or not. So this graph shows that the comparison between simulations and measurements. And then simulation is this continuous blue-red curve. And then the measurements are this, the dotted green and then the black dots. We see that those two agree very well for this glazing. Here, it's the same for this glazing. Looking at even more complex glazing structures, we see the black dots coincide with the blue. The red line corresponds to the green dots mostly. And then the case here too. So that means that using this simulator, it's possible to analyze the attenuation of the radio signals accurately, as we can expect in the measurement. So let's use this simulator more extensively to analyze the different types of the glazings. So here, tons of values. But what I want you to pay attention is this loss value. 1 means 1 dB loss, which means no loss at all. 30 dB means 1 over 10,000 losses, and so forth. And then when we have like only glasses, 2-layer glasses with the air, then we have quite low losses across the different frequencies. But as far as we have soft coated, or this is laminated, then we have greater losses, 30 dBs greater losses. The second type with the 3 glass layers. Again, if we do not have any metallic coating, losses are quite small. But as first we put the laminated glasses, then we have much greater losses. So the 60 dB means almost cutting everything. And then 3-layer glasses, which is typical with the large air gap, which is typical for the Nordic countries. This shows if we do not have any air gap, then the losses are close to 0. But if we have the metal-coated layers, then metal-coated glasses, then losses are much, much bigger. The same here. Finally, with the 4 glass layers, then the losses are very small if we do not have any metallic coated layers. But the losses are much, much bigger if we have the metal-coated layers. Marco, do you think you can complement, or is my explanation sufficient for this purpose?
Thank you, Katsu. Having this table, a lot of glass, a lot of numbers over there, a ton of numbers, as Katsu said. In this study, we wanted to make it like simple thing, focus on the basics. Juha told how we can go further, how we can improve things, but you can see in these tables that how much we have losses in the different glazing structures. And actually it's nice to see that, okay, there are possibilities, as Katsu probably will tell, that we can design for the frequencies from this kind of a frequency point of view as well, concerning the U values of the glazings. This is an informative thing for all what we want to all for share. I think there have been studies for the different frequencies, but to have this wide range of frequencies with the different glazings that presents various glazings used as in Finland, but in rest of the European countries as well. That's what I would like to emphasize on this one.
Good. Thanks, Marco, for complimenting. I mean, the main point is that the more we put the metallic layers, that decreases the U value, which is good. But that also blocks the radio signals pretty much. So don't just look at the U values, but we have to look at also radio wave signal attenuation. That's the main point. So summarizing the losses of the radio signals over the U value, the more metallic layers, of course, we can decrease the U value. That's good. But that also significantly increases the attenuation of the radio signals, which is a headache for the 5G deployment purposes. But what I want to make your attention to be paid is this area where we have no metal, but it's possible to get the U value close to 1.2, which is probably small enough. But we maintain the median loss to be like up to 15 dBs. So this is like a good, probably new idea to realize both the low U value and then the low median losses of the radio signals. So looking a bit more detail about the attenuation of this window for over the frequency, then no metal, of course we have low attenuation loss. 1 metal, 2 metal coatings, we have bigger losses. Of course, one way to reduce these losses is to make a slot, like you have mentioned. And then we just propose alternative method to realize the lower attenuation loss across the frequency. The good point is that over very wide band, from like 1 gigahertz till 100 gigs, we can really realize a very low attenuation of the radio signals, which is, to me, the breakthrough, because I haven't seen this kind of figure in the literature. The same, depending on the incident angle. As I said, the incident angle also decides the attenuation that we realize. And then different color means different incident angle of the plane wave. But if we don't have any metal, again, we have quite low losses. But if we have more metallic layers, then we have greater losses. 100 dBs, it's almost cutting. You don't hear anything in terms of the radio signals. finally, depending on the angle here, incident angle of the incident plane wave, and then we choose 2 gigahertz and 28 gigahertz, which is the future 5G radio signals to deliver high data rate services. It fluctuates a lot, I mean, depending on the polarization of the field. But still, what is apparent here is that if we do not have any metallic layers, it stays mostly up to 20 dBs. But if we have more metallic layers, then it's bigger. So pretty much repeating, but our main takeaway is that if we have metallic layers, we decrease the U value, but we also increase the signal attenuation of the mobile cellular systems a lot. That's a headache for future generation wireless. And hence, we have to have alternative methods to decrease the attenuation while maintaining the U value. And then using multiple layers of the non-metal coated glazings is one of the approaches to realize that one, which is the main takeaway of this work. And then, sorry, I mean, I put the last slide of this glazing, but it doesn't show up here. So we actually have made this like a multiple layered glazings, and then showed it as the 5G glazing. And like it is now displayed in the Nokia premises. And then I'm very happy with this collaboration and then with Marco, but I'm also open for any opinions from you guys about the how promising or how stupid is this idea, and then for hopefully looking forward to further collaboration. Thank you.
Any questions from the audience? Yes, there's.
Thank you very much for this very interesting presentation. I'm a facade designer, and I'm dealing since years with closed cavity facade. It seems to me that this kind of facade would be the most effective to avoid multiple metal layers. When you delete, you have on the inner side, you have the triple glazing. Maybe you delete one of the metal layer, and then it remains only the one metal layer on the inside, because you have this big air gap. So it seems to be the best facade for avoiding these big losses, or not?
Yeah, thanks for the comment. The best from the perspectives of the radio, like cellular scenarios or cellular mobile operators, is no metal coating. But probably it's necessary to have metal coating at some point. So it's like a mixture of the, a metal coating with slots that you have mentioned, or to have like a bigger air gap. Combination of this, okay, I would say.
Let me think in the future. Maybe it's possible to reduce this one layer further by maybe lasering away a part of it.
Yeah, I think that's a good way forward.
That would be maybe investigation necessary. What about if you laser away the inner, this one layer for 10%? How is the effect on the transmittance of this?
Yeah, that's a good item to study. Yes.
Maybe you can study that,
yes,
or have some tests about this. It would be the next step.
Yeah, thanks for the comments. I agree with you.
Anyone else want to take part by asking a question?
So, thank you a lot for the presentation. You consider the insulation metal layer as, let's say, a generic value, but in practice, in coating, there are many different coating using different material with different resistivity and emissivity. So, for example, single silver, double silver, triple silver, but also dop material or other thing. So do you investigate this point? Is there different coating better than the other or worse?
We didn't investigate that one. Yeah, thank you for the comment, first of all. What we tried was just to have like a representative value of the thickness, and then they also like different laminating materials, like just like a single value of the laminating material. So if I have access to like electric parameters of those different materials like laminates, hard-coated glasses, soft-coated glasses, then I think it is really important to look at the variation, because I mean this may be just a coincidence to have lower losses here. But Marco, do you have some more comments?
Yeah, I will comment on the question over there. We asked for the glass manufacturers to give us the recipes, but for some reason we didn't get all the parameters for the layers. So this is a generic, in that sense, study in overall.
Definitely, it makes sense to analyze the like variation of different windows glazing and so forth, because that's what the customers care.
Further questions, comments? If not, thank you very much.
Thank you.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao!